Let us start our lecture today on soil dynamics in module 3 of wave propagation. In the previous lecture, we have seen what are the characteristics of secondary wave and what is called Gutenberg discontinuity and what is the shadow zone for secondary wave inside the earth. And then if any earthquake occurs at earthquake epicenter and waves are traveling through all around through the inner of the earth, then we have seen at different stations P wave and S wave can arrive. In some station none of the waves are arriving, that is the complete shadow zone for both P and S wave, and in some of the zone only P wave arrives, not the S wave, due to this portion of the core which is liquid in nature. Then we have seen surface waves which are traveling only within the earth crust and on the surface media. Then among the surface wave we have seen the characteristics of Rayleigh wave. The typical velocity of Rayleigh wave is about 0.9 times of shear wave velocity, and the behavior also we have seen. Then another type of surface wave is Love wave. The wave velocity for Love wave is again lesser than secondary wave or shear wave, but it is higher than the Rayleigh wave. Then how to locate earthquake's epicenter? We have seen different methods, because in the seismogram where all the waves are arriving, we have seen that first P wave will arrive, then is followed by S wave. There will be sufficient time lag between the arrival time of this P wave and S wave, and then all the surface waves will arrive. That is first the Love wave and followed by Rayleigh wave. From the time difference of this arrival of P and S wave, we have seen how the distance can be computed from the epicenter for different seismogram stations, and using this travel time curve method, if the velocity of this P wave and S wave are not known in the earth crust, we can find out the tentative distances for the epicenter from those stations. Then using those concepts, we can plot it by using the 3 circle method for different seismological stations, and where those circles are meeting, that is the point of earthquake epicenter. So, with that we have come to the end of the module 3, and now let us start with our next module, going to our module 4, which is dynamic soil properties. Now, to start the dynamic soil properties, let me give some background information, or let us brush up some memories about how to represent the stresses in a soil element through Morse circle, which is known to all of us from our undergraduate studies. So, we know if we take a small soil element in 2 dimension, let us say this is sigma vertical, this is sigma horizontal, and we are considering principal stress condition. So, they are principal stresses, obviously there will not be any shear stress, and let us say sigma v is greater than sigma h. Now, how to draw this in terms of Morse circle? That we know, this is x axis normal stress, y axis shear stress, and these are compressive stresses we are considering as positive. So, sigma v is greater than sigma h, and these are principal stresses. This is the value of sigma v, this is the value of sigma h. Then using these 2 extreme points, the middle point is center, we can draw a Morse circle easily. Like that. So, this is the Morse circle. Now, what is the pole of this circle? How to obtain the pole of a Morse circle? Pole is nothing but, let us look at this face where it acts, the horizontal sigma h is acting on a plane which is vertical. So, sigma h is acting on a vertical plane. Let us draw a vertical plane for sigma h, and sigma v is acting on an horizontal plane. So, sigma v is acting on the horizontal plane. Where these two planes meet each other, that junction point is nothing but the pole of Morse circle. So, P, this junction of these two planes where they meet together, that is nothing but pole of the Morse circle. Why pole is so important? Because suppose if we want to know the stress condition at any inclined plane, what are the stresses? So, obviously, that will not be a principal stress, that their normal stress and shear stress both will be present at an angle, say theta with respect to this direction. What does it mean? Pole is that point from which we should draw an inclined line theta, where it intersects the Morse circle. That value of sigma and tau will give us the normal and shear stress at that inclined plane theta. So, that is the use of pole. Why pole is so important? This is the reason, that graphically in a very easy way using Morse circle in 2 dimension. So, 2D Morse circle, we can obtain the stresses on a soil element very easily at any inclination. Suppose we have another soil element which is not of principal stress condition. So, we have shear stresses also, let us say this is sigma 1, sigma 2 and tau is the shear stress, sigma 1, sigma 2 tau, and let us say sigma 1 is greater than sigma 2. If we want to draw this in a form of Morse circle, this is sigma, this is tau. So, sigma 1 greater than sigma 2, and the convention we can consider anti-clockwise moment is positive. So, this one on the face where sigma 1 is acting, this is tau is creating a clockwise moment about the center of the soil element. That means that tau is negative, right. So, the point will be sigma 1 up to here, then here. So, this is the point with value sigma 1 tau as per our convention, as I said, and sigma 2 and this tau is creating anti-clockwise moment. So, this will be positive. So, this is our sigma 2. So, this point will be sigma 2 tau. Now, to draw the Morse circle, we know just simply we join them by a straight line. This will be the center of the circle and this one is the radius. So, this is how we draw the Morse circle for any stress condition like this. Now, how to obtain the pole for this Morse circle? In the same way as I have explained, always remember the sigma 1 is acting on this horizontal plane. So, sigma 1 it is acting at horizontal plane. So, draw a horizontal plane like this. Let me use another color, and the sigma 2 is acting on a vertical plane. So, sigma 2 is acting on a vertical plane. So, where sigma 2 is there, draw a vertical plane, and where these two planes are meeting each other on the circumference of the circle, obviously it will meet on the circumference of the circle, that point is nothing but the pole of the Morse circle. So, this is the pole of the Morse circle. Again, why it is important, as I have said, for any inclined plane to obtain the normal and shear stress, we can draw in the Morse circle that inclined plane with respect to the pole. That is how we can get the normal and shear stress for any soil element. So, this is the representation of two dimensional stresses, but having two dimensional stresses in our static problem or assumptions in the static problem by considering two dimensional stresses for soil is pretty well valid, because when we take any soil element, we consider the vertical stress is one major principal stress and the horizontal throughout the section, cross section remains uniform, we assume in the static problems. So, because of that, we can very well take a two dimensional problem and represent it in the form of a Morse circle. But in case of dynamics, it is not true always. In most of the cases, it is not true that the stresses in the all around cross sectional area of the soil element should be same, because it may happen many a times because of your propagation of the wave, basically the S wave, your direction of particle movement perpendicular to the direction of S wave can be in a particular direction, say in the east west direction instead of north south direction. In that case, the stresses in that east west direction will be different than the stresses in the north south direction for the soil element. So, for dynamic problem, it is not correct to consider a two dimensional stress problem or two dimensional stress element and draw it in form of Morse circle like this and to get stresses for soil element at any inclined plane. So, what to do? To address these issues of three orthogonal different stresses for a soil element in actual problem of dynamics, that is where sigma 1, sigma 2, sigma 3 are not same, they are altogether different. How to address that problem? Let us see. So, what we are now considering, let me draw this first. 3-axis system, first I am drawing 3 orthogonal axis system, say 1, 2, 3. 3 principal stress direction, let us consider. Now, one element in 3 dimension, now I am taking, this is one element in the 3 dimension. Let us say this origin is O, this point is A, this is B, this one is C. As we have taken, these are the principal stress direction. What does it mean? I am considering on this plane, let me draw it individually so that it is clear to us. O, B, C on this plane, let us say we have normal stress sigma 1 and this is the direction of positive we are considering, compression positive. So, sigma 1 is what? The principal stress in direction 1 acting on this plane. Okay? Now, on this plane O C A, O C A, here we are considering sigma 2 as the principal stress in the direction of 2, and on this plane O A B, let us say this is sigma 3, this is the positive direction. So, these are the three principal stresses acting on the soil element, and let us say sigma 1 is greater than sigma 2 is greater than sigma 3. So, what we call them? This is major principal stress sigma 1, sigma 3 the lowest one is minor principal stress, and sigma 2 is called intermediate principal stress. Now, if I want to find out the normal and shear stresses on any inclined plane with respect to these three orthogonal axes, how we can determine that? So, let us say on this plane, that is the plane ABC. Can you see this? ABC. On this plane, any inclined plane, I want to find out how much is normal stress, how much is shear stress. Shear stress say tau n and normal stress say n, where n is the nth plane. I am considering this inclined plane. So, on this inclined plane, how much normal and shear stresses are acting, we want to find out. And inclination of this plane on which we want to find out the normal and shear stress, this arbitrary plane, nth plane, is such that its angle with respect to axis 1 is say given by theta with respect to nth plane, and axis 1 is given by like this. The another angle it makes with axis 2 is given by say theta n with respect to axis 2 and theta with respect to n axis 3. So, these are the three angles made by this plane nth plane with respect to axis 1, axis 2 and axis 3. So, what we can write from this, we can write down the triangle OBC. Let us keep the figure here. So, it will be easy for us to follow. This triangle OBC, this area of the triangle is nothing but how much? We can express it as this inclined plane area ABC times cosine of n1, because n1 is the angle between this nth plane with respect to axis 1. So, the projection of this plane on this 2, 3 axis will give us the projection of this area on this plane will give us the area OBC, right. Similarly, the other areas like area OAC, this area should be area ABC times cosine of that angle N2, because this is projection on 1 and 3 axis. 1 and 3 axis, it will be the projection cosine of angle this one makes with respect to axis 2. Projection of that on this will be the area, and triangle OAB, this area should be triangle ABC times cosine of angle between that nth plane and axis 3. So, nth plane, that direction is nothing but perpendicular to this one. Okay. So, that axis nth axis. n with respect to 1, n with respect to 2, n with respect to 3. These are the 3 angles. Now, the normal force acting on this inclined plane ABC is sigma n. So, from which what we can write? The total normal force will be the normal stress times the area of that inclined plane, which will be nothing but equals to sigma 1 times OBC cosine n1 plus sigma 2 times OAC cosine n2 plus sigma 3 times OAB cosine n3. Total normal force I am obtaining. Total normal force on nth axis or nth plane, that should be equal to this one, that is component of the normal force what we are having on plane OBC. So, on plane OBC we have total normal force is sigma 1 times this area, then its projection on the nth plane. So, that is why cosine of n1. Similarly, for the other two, sigma 2 OAC times projection of it on this and sigma 3 OAB times projection on this. So, now if we put OBC, OAC and OAB expressions from here, from this relation in this expression, then ABC from both the sides will get cancelled. So, final expression from this relation we will get sigma n equals to sigma 1 cosine square n 1 plus sigma 2 cosine square n 2 plus sigma 3 cosine square n 3. So, this is the expression by using which mathematically we can obtain the normal stress on any nth plane from the given 3 principal stresses sigma 1, sigma 2, sigma 3, and knowing the angle of that normal plane with respect to those principal stress directions. Now, mathematically we have obtained this. Let us see how the shear stress we can obtain now. So, resultant stress on that inclined plane ABC, let us say that is sigma r. The resultant stress is nothing but normal stress square plus shear stress square, right? And the resultant force F r should be this resultant stress times the area of that plane. Now, what is the force acting on this plane OBC, that is principal planes, that is sigma 1 times area OBC, which is nothing but sigma 1 ABC cosine n 1. Similarly, the other 3 also we can write, like force acting on OAC is sigma 2 times OAC, which is sigma 2 ABC cosine of n 2, and area OAB should be sigma 3 times OAB sigma 3 ABC cosine of n 3. Now, this resultant force F r square is how much? Summation of squares of the 3 orthogonal forces, right. So, it should be equals to F OBC square plus F OAC square plus F OAB square. So, on simplification what we will get, this FR square is equals to sigma 1 delta ABC cosine of N1 whole square plus sigma 2 ABC cosine of N2 whole square plus sigma 3 ABC cosine of N3 whole square. Therefore, sigma r square, this ABC square we can cancel from both the sides, it boils down to sigma 1 square cosine square N1 plus sigma 2 square cosine square N2 plus sigma 3 square cosine square N3. This is another relation we can obtain. So, two relations we got, we need three relations to draw Mohr circle, because we have to obtain the three center of the circles. Now, how to represent these 3D stresses in the form of 2D Mohr circle? That is, we are representing now 3-dimensional stresses in 2-dimensional form. How to do that? Let us see. So, the third relation which must follow is the cosine rule of angles. What is that? Cosine square N1 plus cosine square N2 plus cosine square N3 must be equals to 1. Right? This is the cosine rule of any inclined plane with respect to the 3 orthogonal axis system. Fine. Some of the books they denote it by L, M and N, L square plus M square plus N square equals to 1. So, using these three relations, what are those three relations? I have highlighted it here. Let me put it once again, so that now we know. Yes, this is one relation, this is the second relation, this is the third relation. Using them, now we can simplify these three and write that cosine square N1 tau n square plus sigma n minus sigma 2 sigma n minus sigma 3 by sigma 1 minus sigma 2 sigma 1 minus sigma 3. On simplification, one can get this expression using those three relations. Similarly, cosine square N 2 should be tau n square plus sigma n minus sigma 3 sigma n minus sigma 1 by sigma 2 minus sigma 3 sigma 2 minus sigma 1, and cosine square n 3 can be solved as tau n square plus sigma n minus sigma 1 sigma n minus sigma 2 by sigma 3 minus sigma 1 times sigma 3 minus sigma 2. Now, how does it help us to obtain the radius and center of Mohr circle? What is the nature of these three values? They must be greater than or equals to 0. They cannot be negative. Am I right? This is a cosine of an angle square. So, it never can be negative. This also must be greater than or equal to 0. This also must be greater than or equal to 0. Now, what we can look here, that sigma 1 is greater than sigma 2 is greater than sigma 3. So, this parameter is always, this is positive, this is positive, positive. Sigma 2 is greater than sigma 3, this is positive, but sigma 2 is less than sigma 1. So, this is negative. So, this product is negative. Okay? So, to obtain this as positive, this also must be negative. Whereas, this one sigma 3 minus sigma 1 will be negative, sigma 3 minus sigma 2 will also be negative, but product will be positive. So, no problem, we will get a positive. What does it mean? If we simplify these expressions further, it can be written in this form: tau n square plus sigma n minus sigma 2 plus sigma 3 by 2 whole square should be greater than or equals to sigma 2 minus sigma 3 by 2 whole square. The second relationship gives us tau n square plus sigma n minus sigma 1 plus sigma 3 by 2 whole square should be less than equals to sigma 1 minus sigma 3 by 2 whole square. And the third relationship will give us tau n square plus sigma n minus sigma 1 plus sigma 2 by 2 whole square should be greater than equals to sigma 1 minus sigma 2 by 2 whole square. What does it mean? Where from they have come? Let us put it back here again. From this relation, as I said, this is always positive. It will give us this one. This, if you simplify, if you take it here, it will be positive. You will get this greater than equal to sign for this one. Whereas, for the second one, to satisfy this relation, this is being negative, the relationship will come like this. If you simplify, you will get. And the third relation one is, this is positive. So, if you take it here, you will finally obtain this relationship greater than equals to like this. So, from these three relationships, now we have to see how we can draw these 3D stresses in two-dimensional Morse diagram form. So, that we will continue in our next lecture. Now, coming to the three-dimensional stresses in soil element, we have seen this in the previous lecture, that the three-dimensional soil element is, we have represented like this with three directional principal stresses, sigma 1, sigma 2 and sigma 3, major principal stress, intermediate principal stress and minor principal stress, and the corresponding direction cosines with respect to any plane, nth plane, with respect to those principal stress directions we have seen, and from which we had derived the expressions for angle of this cosine square of that nth plane with respect to principal stress direction 1, 2 and 3 to satisfy these conditions, from which finally we got the expressions like this, where this tau n is nothing but the shear stress on that nth plane on which we want to find out what is the normal and shear stress. Sigma n is the normal stress on the nth plane, and other things we have already defined. So, from these expressions, what we can say, if we want to represent it in graphical form, in the form of a circle, if we look at these equations very carefully, these are nothing but equations of a circle. This is also equation of a circle, equation of a circle, equation of a circle, with which these are the center of the circle and these are the radius of the circle, right. If we recap our memories of equations for general equation for circle, we can easily remember these things. So, if we want to draw these circles in a 2D plane, how they should look like, let us draw it. So, this is our normal stress direction, shear stress direction. Now, first equation, let us look at it. Let us take one by one. This is sigma 1 and sigma 2. So, these are the two principal stresses, and what we have considered, sigma 1 is greater than sigma 2 is greater than sigma 3. That is the condition we have taken. So, let us plot those principal stresses. Say this is our sigma 1, this is sigma 2. So, with these two principal stresses, we can draw a Mohr circle with the center of the circle at sigma 1 plus sigma 2 by 2. So, this is one Mohr circle which is satisfying this equation. Let us look at here. This is the center of the circle, sigma 1 plus sigma 2 by 2, and this is the radius of the circle, sigma 1 minus sigma 2 by 2. That is what we have drawn. Then let us plot another principal stress, which is, let us say, sigma 3. Say this point is sigma 3. Our order we have seen, sigma 1 is greater than sigma 2, sigma 2 is greater than sigma 3. Now, with these 2 points, sigma 2 and sigma 3, we can draw another circle, another Mohr circle. So, for this circle, what is the center? That is sigma 2 plus sigma 3 by 2, and the radius is sigma 2 minus sigma 3 by 2, which is nothing but coming from this first equation. Now, we can draw another Mohr circle by considering this two principal stresses, sigma 1 and sigma 3, and the center of which will be sigma 1 plus sigma 3 by 2, and the radius will be sigma 1 minus sigma 3 by 2. So, the third circle should be something like this. Fine. Now, the state of stress of any point which we are trying to find out on nth plane. So, that point, if we want to put on this Mohr circle graphically, where it should come? That point must lie in this zone. So, it must be somewhere here. So, let me shade the area first, then I will explain why. The state of stress on any plane, any nth plane, must lie on this shaded area, not anywhere else. Why? If we look back to our equations of this circle, so what does it mean? The state of stress on that nth plane from this equation between sigma 2 and sigma 3, that is the Mohr circle between sigma 2 and sigma 3, whatever the circle we have drawn, the state of stress, that point must be outside or maximum on the periphery of this circle or circumference of the circle. That is what this inequality signs denotes, right? Equal sign shows that point can lie on the circumference of the circle. The greater than sign denotes the point can lie outside this smaller circle between sigma 2 and sigma 3. Clear? What about the second equation says? Second equation gives us that the point must lie within the circle of sigma 1 and sigma 3 with a maximum boundary condition of equality sign, where the point can lie on this circumference of the circle. So, when the equality sign holds, at that time the point will be somewhere on this circumference of the circle. Otherwise, always it must be within this circle of between sigma 1 and sigma 3. What is the criteria we are getting from the third equation? That the point on that nth plane, again they must be within the circle, the point on nth plane must be outside the circle between sigma 1 and sigma 2. The equality sign again says that it can lie maximum on this circumference of the circle, otherwise the greater than sign denotes it should be outside or at this point. So, from these three equations, what the graphical representation of the three dimensional stresses are in a soil element, this is the graphical representation in 2 dimension, means 3 dimensional stresses we are representing in 2 dimension using this concept of Mohr circle, where any state of stress must lie in this shaded zone, not in any other areas. And obviously, if you find out the values of sigma and tau for that point, you will get your normal stress and shear stress for any nth plane. Fine. So, this is the way graphically we can find out the state of stress on any nth plane for a case of 3 dimensional soil element. Okay. So, let us look at the slide here, that is what it is given, Mohr circle representation of 3 dimensional stresses. Now, when we are talking about the determination of dynamic soil properties, as we know, similar to our static determination of static soil properties, we can broadly classify the tests in 2 categories. One is field test or in situ test, another one can be laboratory test. Okay. So, among field test for the determination of dynamic soil properties, we can again subclassify them into 2 categories. One is called direct test, another is called indirect test. What are the different direct tests? One is seismic reflection test, another one is seismic refraction test, another one is spectral analysis of surface wave test, which is in short called SASW. If you look at here, spectral this S, analysis A, surface S, W. So, SASW test, and a modified version of this SASW test are also available nowadays, that is called MASW. What is MASW? The same spectral analysis of surface wave, in that case it is multi-channel. So, that is why MASW, but the methodology of the testing and principle everything remains same, only difference is instead of a single channel we use multi-channel. So, that is why MASW also you can note down with this. Then another direct test is called seismic cross hole test, and another one is called seismic downhole or uphole test. So, these are the different types of direct field test for determination of dynamic soil properties. And what are the common indirect test? Like SPT, that is standard penetration test, cone penetration test or CPT, Baker penetration test BPT, etc., Venn shear test, etc., etc. As you know, these are the common test, field test for static condition also. So, to determine the static soil properties, these are the tests. So, that is why we have mentioned here or classified it under the category of indirect test, because these static field test also helps us to correlate with the some of the dynamic soil properties. So, as we progress in the lecture, we will see how the correlations holds good for determination of dynamic soil properties from these static tests. So, now for different types of direct test for this field testing, what is the basic methodology? That we have to create a vibration in the soil. That is the basic criteria to do a direct test for the dynamic soil properties. So, to create an impulse or a vibration within the soil, there are various types of methods. These are shown in the picture here. The first one is by using shallow explosives. If we use some explosive at a very shallow depth below ground, then the waves can get generated and then we can record them using different direct test method for the determination of dynamic soil properties. The second one is by using vertical impact on the soil directly like this, and another type can be by using horizontal impact like this. If you put a log, so wooden log is kept, then on that you create or hammer it, then by providing that you are creating a vibration in your soil which gets propagated. So, these are the sources of vibration. These are called sources of vibration for different seismic geophysical test or the direct test. So, now let us come to the major criteria or characteristics of various direct test. The first one is seismic reflection test. As the name suggests, here we use the principle of reflection of wave. We have seen wave propagation, the three components: reflection, refraction and the incident wave, three components of waves. So, here the concept of reflection of waves are used. This S is nothing but source, that is where you are creating that disturbance or vibration in the soil by using any of the above three methods, just now what we have described. And the point R is called receiver. So, these are receiving the disturbance created at this point, followed as a waves through the soil media, and which is finally recorded at the receiver R. Suppose if we have layered media, layered soil media like this, and these are horizontal layers, let us assume first, and the top layer is having a primary wave velocity or P wave velocity, say Vp1, and the second layer is having a primary wave velocity or P wave velocity of Vp2. Then obviously, the waves which are traveling, some of them will get reflected back in the first media and some of them will get transmitted in the second media. So, and I is the angle of incidence with respect to vertical. So, this angle between them is 2I. So, it shows path for incident ray and reflected ray of P wave from horizontal layer boundary, and how much time is required for the wave energy to come from this point S to R. If their horizontal distance on the ground is given by x, then the time T d is given by distance of travel by the wave velocity in that media. Because primary wave, as we know, this is the wave which will travel fast, right. So, obviously, first one which we are recording in our time receiver, that T d is nothing but x by Vp1. And the angle of incidence of the impulsive energy travelling downwards, that I can be expressed as tan inverse x by 2h, which is very simple from this triangular distribution. From the geometry we can write it very easily. And the time taken by the reflected wave by putting all this relationship T r, that can be, the previous time was the for the direct wave and this is for the reflected wave. So, direct wave actually goes directly from here to here. So, T d is this one, whereas reflected wave is the next one which will arrive at your receiver. So, that time T r will be something different from T d, that will not be same. So, you can easily compute from the geometry of the figure what was shown. This is the expression for distance of travel by wave velocity, that is reflected wave time taken. If you plot that time versus the distance relationship, obviously, the direct wave will be a complete linear distribution with respect to time versus x, right. Whereas, the reflected wave, it will depend on your thickness of the media and of course, the wave velocity within that media. So, it will take a shape like this with an intercept on the t axis like this. So, the thickness of the upper layer can be computed if you simplify this expression and put it in terms of h, you will get the expression in terms of h like this, in terms of time taken by the reflected wave and the primary wave velocity in the first media and the x distance between the source and the receiver. Now, suppose if we do not have the horizontal layers, so nice horizontal layers, but we have inclined boundaries or irregular boundaries, then how we can measure the thickness of a particular layer and of course, the VP1, either of these two. In the previous case, in the time travel variation for direct and reflected wave, we can measure the VP from the slope of the curve. That is direct wave and reflected wave, when the slope of the two curves are matching, that is the slope which will give us the value of VP. And then using that, this value is known to you, this value is known to you, you can compute the thickness of the upper layer. But if the layers are not horizontal, but inclined like this, what will happen? So, this is the layout for the source and receiver for that seismic reflection test with inclined layer boundary. In this case, suppose this is the source point and A and B are the two receivers at the both the sides of the source at a distance of x A and x B on the ground surface, horizontal distances. And alpha is the inclination of this layer with respect to horizontal, and VP1 is the primary wave velocity of this top layer. Then this VP1, if we talk about the direct wave, that will be equals to this distance by time taken for the direct wave to arrive at station A and the time taken to arrive at station B. They must be equal to VP1, they must equate each other, right. And if receiver A is placed at the source, then x A is 0, and then the equation sin alpha, this expression for alpha can be expressed like this, which on simplification will give us this expression. In this case also, we can plot the travel time curve, that is time versus distance, for two cases, and at one place they will meet each other. That is, you plot the time for receiver A at left hand side of the y axis and for receiver B on right hand side of the y axis, then start drawing the t versus x plot. At the junction of them, the slope of the curves will give you the value of VP, from which you can find out the alpha inclination of the layer. So, with this we have come to the end of today's lecture. We will continue our lecture in the next class.